So here's an article that I thought we could start with that covers a more serious consequence. We've gone over things like how software performance issues or security vulnerabilities have a real world impact on you and the people you care about. But let's think about like society as a whole, right? So if you live in the States, you have a vested interest in being safe, in your own country and having as much capability for, say, the army or the police or other groups that are determined to be in charge of your safety. You have a vested interest in ensuring that they have the maximum resources available to keep your safety at hand. This is not just true of the States. Obviously, any country you live in, you're going to want to be safe in that country. And so you're going to have an interest, at least for yourself, if not for the people you love, to ensure that the people who are responsible for your safety have the things they need to keep you safe. And when they do not, that is a problem. And I hate to break it to you, but if you're a programmer, you are directly responsible for the safety of at least some people in your circle. Let's narrow it down to maybe even just like your localized area. We've gone over this before, but let's tackle an article here. I'll read it out like we normally do. Unfortunately, these things get bogged down by reading and statistics and data. But again, I'm just going to very clearly state that nobody has the balls to get on camera and cover these topics and discuss the data the way that I am doing it. Because people are usually too chicken shit to face the fact that they might be responsible for some of these extremely serious problems. I, on the other hand, will like to face it head on, expose the problems, and find ways to deal with it. So, as much drudgery as we're going to go through, etc., like most of these streams tend to bring up, there's like a lot of boring stuff we have to get through. I will go through them nonetheless, because I feel it is my imperative duty to do so. Okay. This first article, Machine Failing: How Systems Acquisition and Software Development Flaws Contribute to Military Accidents. So this was written around end of 2024, beginning of 2025 from the University of Texas at Austin. How does software contribute to military accidents? The stakes are high. During the Cold War, computerized early warning systems produced near-miss nuclear crises. In the future, military AI applications could fail with devastating consequences. To eliminate the causes of military accidents, existing studies apply normal accidents and high reliability organizations' theories. While these frameworks are helpful, they neglect the military system acquisition process, which often outsources software development to contractors and limits input from military end users. Now, I can already hear the rebuttal, right? And the rebuttal here would be, wait, but this is talking about the way that the military reviews and accepts third-party software resources to introduce into their military systems. But you can note that there is a distinction here. It is often outsourced to contractors. Some of those contractors might be you, if not already. So my immediate rebuttal to the rebuttal would be, it doesn't matter. If you were to be hired by the military as a contractor to make a judgmental determination of a third-party software, how capable would you be? And if you're someone who lives in the easy button world, where your comfort and preferences and your vibes-based programming are the top of your, say, desired paradigm to solve, I'm going to argue that you are not very capable of making a good judgment value on what should be introduced into military software versus not. By contrast, the software development lifecycle theory expands the causal timeline of accidents beyond decisions made on the battlefield to those made decades earlier in software design. And I just want you to really drill in on the words. Like, the words here are important. First of all, there's a time-based factor, which is it is a ticking time bomb. You have potentially decades of time that go by between the decision to include a piece of software and the time it takes for it to explode in a military setting, quote unquote, right? Furthermore, software design is not always the same as software code. And I want to bring this out because we're going to get into why the cognitive ability of programmers is indeed, and I would say in fact, and I would say I've proven this time and time again, it is indeed being neutered, which is a necessary entailment of software design. You must have some level of ability to have cognitive ability to design in order to do software design. We're going to get into that. Serving as an antecedent account of how software contributes to military accidents. Illuminating dynamics overlooked by the two dominant approaches, this theory is supported by 4 cases. The 1988 USS Vincennes, I'm not sure how to pronounce that, I apologize, shoot down of an Iranian airliner, the 2003 Patriot fratricides, the 2017 USS McCain collision, and software upgrades in the 2021 Kabul airlift. On August 21st, 2017, the USS John McCain crashed into an oil tanker near the Strait of Malacca, resulting in the death of 10 sailors and marking the Navy's worst accident in 4 decades. While the Navy initially blamed the incident on the McCain's crew, later investigations pointed out problems with the ship's navigation software. In fact, the Navy's own review of the crash stated, "There is a tendency of designers to add automation." There is a tendency of designers to add automation without considering the effect to operators who are trained and proficient in operating legacy equipment. Safety-critical software systems come with high stakes. At present, maritime forces rely on navigation software like the one used on the McCain, and an accident at sea could be one of the most likely triggers of a military conflict between the United States and China. So I just want you to consider this for a moment. What could happen if, and this is not beyond the realm of possibility, as a matter of fact, I would argue that it's extremely possible. What would happen if you create a mission-critical React application that NPM installed a stupid NPM library with a huge vulnerability, causing a military accident which necessarily led to a global war? You cannot, in good faith, tell me that that is not possible or that is an outlandish statement to make. You would have to be the most naive, ridiculously idiotic person on the planet to think that there is zero possibility of that happening. During the Cold War, accidents involving computerized early warning systems produced numerous near-miss nuclear crises. In the future, military systems that incorporate new advances in AI and other emerging technologies could also fail, bringing devastating consequences. How does software contribute to the risk of military accidents? Existing scholarship on the safety risks of military technology systems draws on debates between normal accidents theory and high reliability organizations theory. The normal accidents approach argues that the causes of accidents in highly complex and tightly coupled technological systems are deeply embedded in the systems themselves. Tightly coupled systems require centralized authority because small mishaps can rapidly escalate into major disasters. But problems in complex systems demand responses by local decision makers who understand how the system works. The tension between these two imperatives results in unavoidable accidents. Under normal accidents theory, accidents are inevitable in software-intensive military systems because they are very complex and tightly coupled. For instance, one expert on AI governance predicts that normal accident problems will be particularly acute in military AI applications. For instance, one expert on AI governance predicts that normal accident problems will be particularly acute. If you don't know what acute means, I would like for you to go up and look up the definition of acute in military AI applications. The high reliability organizations literature, in contrast, posits that certain organizations can effectively manage the risks of hazardous technologies. Studies in this tradition emphasize the importance of organizational culture, such as deference to expertise and dedication to learning from failures, as well as flexible organizational structures that permit authority to be centralized and decentralized depending on the situation. As evidenced by studies of the U.S. Navy's nuclear aircraft carrier community and submarine community, certain military organizations have demonstrated excellent safety records with complex, interdependent technology systems. Scholars have proposed the high reliability organizations model as a way to manage the risks of autonomous weapons. There is an implied situation here. So essentially what they're saying is that a good way to deal with the inevitable increase in problems that things like AI will introduce into military operations is to have a more flexible structure with more expertise. How do you get more expertise? Everyone has to start somewhere. If we relate it to the programming space, that means you as a junior are one day going to be relied upon to be the senior expert. That means that you as an executive or someone in technical leadership have to be aware that you cannot just dismiss or hand wave away junior developers and replace them with AI, because one day that AI is not going to be able to make the decisions that junior developers need to get to be able to make as they gain the experience that AI necessarily removes them from being able to take because you hand waved it away. The military has some people who are at least able to see that this is going to be a problem and have come up with an organizational structure that at least potentially mitigates the problems that are going to come up with it, with this kind of stuff. Even without AI, you can still make the same argument that you need to have people who understand their domain, people who do their jobs, people who execute on their job description, people who do the uncomfortable factors that don't give them the good vibes and the feelings that they're being productive and so on and so forth, that a lot of cushy programmers who are frankly spoon-fed with silver spoons and get to benefit from, and you could say privilege, whatever you want to call them, they get to enjoy all of these things and complain about their, productive output or the way that they vibe with the code that they produce and whatever. This is all meaningless nonsense that has nothing to do with the actual job at hand. The military at least has some people who recognize this. We should be able to recognize this as well, and I don't think we are. To be sure, these two approaches have produced valuable insights on the causes of military accidents, yet the applications of normal accident and high reliability organizations theories to software intensive military systems share a drawback. Their scope of analysis is confined to the actions of military organizations only after software systems have been fielded. This means that they neglect the initial phase of software acquisition and development when critical safety decisions are made. And I would argue that this is also true in the software world in general. People very rarely think of the long-term consequences of the build tool chain or the library or the framework or the language that they're using. Not only do they neglect to look at the long-term consequences, and by the time those consequences rear their ugly head, it's too late. But furthermore, we have made it so that most of our programmers do not even know how to make a judgment value on those long-term consequences to begin with. They don't even know what questions to ask. It also means that the existing literature does not account for the activities of the defense contractors that develop most of the military software. Taken together, these considerations point to the importance of the military software acquisition process. If this process limits feedback from military operators to end-stage testing and evaluation, for example, linear waterfall models, when it is too late to change fundamental systems designs, accidents are more likely. These acquisition pathways often yield confusing human-machine interfaces and limited adaptability to hidden vulnerabilities that emerge from operators using the system in the field. In this article, I propose software development lifecycle theory as an alternative way to explain how software contributes to military accidents. And you can make the same exact argument for, say, executive leadership or programmers or technical leadership, whereby they think in short-term stints, 1 to 3 years. Usually, serious consequences of software or programming decisions take in the sometimes decadal. And again, I have gone over the scientific and academic studies that show that a lot of vulnerabilities go purely unnoticed or unreported for up to a period of 10 years before they're even exploited, and then a further few years before they're patched. These things do not live in the span of 1 to 3 years. Get that sweet VC exit money, bro. I'm not going to be around for 3 years because I don't want to stick around for this company, or I don't think this company cares about me enough to keep me around for more than 3 years, or, insert any number of reasonings you have for this short-term, myopic, and frankly, dangerous viewpoint. So I'm going to take a moment and I'm going to call out all these people who think this short-sighted and myopically. You are fucking up my future. Fuck you. And you're not just fucking up my future, you're fucking up the future of my kids, my family, and yours. And if you don't give a shit about your short-sighted viewpoints on the tech industry and whether something will exist or function or behave appropriately or cause problems beyond a 1 to 3 year time frame, then you're a piece of shit. Get your head out of your ass and think about the long-term consequences. Now here's the positive side of this. You don't have to lose any amount of money. You can actually make more money by considering these things. And that goes from the bottom all the way to the top. Whether you're a junior programmer to an executive, if you take these things into consideration, if you account for the fact that you might want to keep programmers around for longer than a 1 to 3 year stint, if you want to consider the fact that your sweet Series A, Series B, seed round, whatever the hell it is, if you want to stick around further than that and make more money, then you probably should be focused on the outcomes of the quality of your software, not the number of features, not whether hardware can mask issues, not how fast you got to market. None of those things ultimately matter. And it's even more important if you actually care about yourself, your family, and the people around you. Okay. By focusing on patterns of software procurement and development, software development lifecycle theory sheds light on causal factors that affect military accidents often overlooked by the normal accident and high reliability organization's perspectives. Consider as an illustration the failure of a Patriot missile defense system to intercept a Scud missile that struck a U.S. barracks at Dhahran, Saudi Arabia, in the last days of the Gulf War. The missile's impact caused the deaths of 28 soldiers, more than one-third of all U.S. service members killed in the war. Army investigators attributed the breakdown to a timing error in the computer software designed by Raytheon. Long continuous operation led to loss of precision in tracking incoming missiles. So again, I'm just going to be perfectly blunt. I've talked to people like Chris Griffin and others on social media and on stream, and I have made this exact argument. When it comes to military operations, like for example, the software that runs on a missile, do you think that nation-state actors are happy or unhappy when we use the stupidest, slowest, easy button paradigms to execute software on our missiles? Clearly, they are happy and they think we are stupid and they like it, because what it necessarily means is that our missiles cannot perform at the operational level that they're required to make a proper defense against missiles that are being made by nation-state actors who do not care about the vibes or the good feelings or the productivity level of any of their programmer. Most nation-state actors outside of the Western world simply do this. Programmer, I do not care how you feel. You are going to get this job done, and you're going to do it with quality metrics in terms of performance that match our requirements to exceed any of our potential enemies. And if you don't, well, maybe you're not around tomorrow, or maybe one of your family members isn't around tomorrow, or whatever threat that other nations might want to use to enforce these things, because they do not care about the same things that you have the privilege of caring for in Western society. As a result of that, and this is the case I've made, and people said I was stupid for making this case, 28 soldiers lost their lives because of a software error that could have been avoided. Now, can I say that this is because these programmers at Raytheon did vibes-based programming? No, I cannot say that. What I can say is that it is very clear that there are consequences to not caring about the quality and performance as one of the fundamental principles, pillars of what you're producing. You have no idea when the code you're generating is going to cost the life of even one person. And if you cannot see that, you're a piece of shit. Crucially, technical specialists were aware of the issue and had even developed a software patch. But the upgrade was not prioritized because they discounted the possibility that operators would keep the computer running for long periods without a reboot. The accident was not normal. Despite tight coupling and complexity, the cause was well understood and a fix was available. Nor could it have been prevented by the Army improving its organizational culture and structure. The computer malfunction was a product of considerable disconnect between Army users and software contractors in the Patriot's development process. I'm going to take a hardline stance here. This is a very charitable interpretation of what happened. This happens all the time. I am not oblivious to this fact. I have been involved in bad communication methods between a programmer and someone in leadership who is not a programmer. Something bad happens. And yes, communication broke down along the way. It was not appropriately discussed. Insert any number of communication issues. That is a constant battle. Here's my hard stance argument, however. The entire problem of this software failing in the manner in which it did could have been avoided, period. And if my argument were taken to its most extreme measure, which is we should be requiring programmers to have a much better understanding of the pillars of what the hell they're doing, I do think this could have been avoided and no communication would have been needed at all. That's my argument. This theory is supported with 4 case studies. The 1988 Vincennes, I'm butchering that pronunciation, I'm sure, incident in which a U.S. naval ship accidentally shot down an Iran Air civilian airliner. The 2003 Patriot fratricides at the beginning of the U.S. war in Iraq, the 2017 USS McCain collision, and software performance in the 2021 Kabul evacuation. In each case, the choices about software development by senior procurement officials and defense contractors were central to how software contributed to accident risks. This is not to say that human error played no part. Rather, the way in which these military systems were developed set end users up to fail. The article makes 2 main contributions. First, scholarship on military accidents has been preoccupied with the clash between the normal accidents and high reliability organization frameworks. Since Scott Sagan's formative application of these frameworks to nuclear command and control accidents, this literature has seen very few theoretical innovations. Departing from the normal accidents, high reliability organization dichotomy, this article presents a novel approach to exploring the sources and limits of safety in military technology systems. Okay. Second, this article has direct implications for the risk of emerging technologies such as AI. In recent years, leading scholars and policymakers have likened the safety hazards of autonomous military systems to the Cold War's nuclear close calls, many of which were linked to false alarms produced by technological systems. For example, Michael C. Horowitz, a University of Pennsylvania professor who serves as the director of the Department of Defense's Office of Emerging Capabilities Policy, re-examined the Cuban Missile Crisis with autonomous naval ships in the mix, giving significant attention to the accident risks of uncontrollable systems. These analyses appropriately highlight specific features of AI-enabled military applications, such as enhanced levels of autonomy, but they gloss over the simple fact that these applications will be implemented as software programs. So you have a dual issue here, which is you have, on the one hand, you already have existing problems with non-AI pieces of software, and now you introduce uncontrollable or far less controllable pieces of software in the form of AI with the same problems continuing to exist. While AI will bring novel risks, learning from past software-intensive military systems should serve as a foundation for comprehending the risks of military AI applications. Okay, what is the software development lifecycle? How does it affect military accidents? Typically, a software failure is defined as the inability of code to meet performance requirements. When post-accident investigations assign blame to the crew by noting that software systems performed flawlessly, as was the case with the Navy's report on the McCain crash, they rely on this narrow definition of software failure. In contrast, the normal accidents and high reliability theories emphasize that software can contribute to accidents even when it performs how it is supposed to, by influencing the connected structures and organizations tasked with managing hazardous technologies. These 2 prevailing organizational theories of safety and technological systems, therefore, offer a broader conception of software failure in military accidents. The first approach contends that normal accidents occur in software-intensive military systems due to tightly coupled and highly complex structural elements, which we've gone over. Even if software works as coded, novel and unexpected interactions between battlefield conditions and such systems can snowball into unavoidable crises. For instance, In a 1979 false alert involving missile warning computers, the United States initiated retaliation measures based on mistaken reports of a major Soviet nuclear attack. This near miss was produced by coincidences that would have been difficult to reasonably predict, including the insertion of training tape data at the same time as a momentary circuit failure in a ground station. This is a very fair argument. It almost doesn't matter how performant your software is. You can almost never determine when a user will use something in exactly the right circumstances that you couldn't have thought of. That is more of a design issue than a coding issue, although coding does lend itself to making these design issues or potential user, let's call it abuse issues, worse or not as bad if you appropriately tackle with the coding to begin with. But if all things are equal, this is a fair argument. The second approach, rooted in high reliability organizations, also posits that accidents in software-intensive military systems are rooted in the organizational structures that manage these systems. High reliability organization scholars claim that certain organizations can reliably prevent systems accidents if they maintain certain qualities, such as deference to experienced operators, devotion to learning from failures, and commitment to safety. Studies of the U.S. nuclear Navy, for instance, have highlighted the experience level of operators and cultural commitments to safety. Notably, the autonomy of experienced frontline operators to circumvent certain bureaucratic procedures is one way high reliability organizations maintain system safety. So I just want to make note of this because I thought this was a good corollary to you as a junior developer, if you're a junior developer. Even the military recognizes that the bureaucracy can get in the way of executing on something that is proper within the context of the person who is executing it and what they deem to be proper. You as a programmer, whether you're junior or not, but even as a junior, have a responsibility to execute on your job. And that means that instead of being afraid of the bureaucracy, instead of being afraid of the intermediate or the senior or the technical leadership or the executive or whoever it is externally influencing the decisions you make, you should not be afraid of them. It is your job to try and maintain, for example, system safety or system performance. And as a junior programmer, you have just as much ability and rights, if you will, if not duty, to ask the same questions that a senior programmer would have if they looked at something and went, wait, why are we doing this? So don't depend on other people to do that job for you. You're far more capable than you have been told you are, and you should. You ought to. It is your duty to. While these two schools of thought are helpful for understanding how software affects military accidents, their focus is on unpredictable interactions or operator inadequacies that trip up software systems after they are in operation. Less attention is paid to the system acquisition and development phases before militaries even field these technologies. Yet, software safety specialists have identified that the bulk of safety-critical decisions are made during the initial phase of software design and requirement specification. Based on one study of military aviation mishaps, the concept development step accounts for 70 to 90% of safety-relevant decisions. I'm going to expand this argument further. If it is true of military, then it is true of any industry, including haphazard industries that you might be working in. Your decision of, hey, let's just use React because it's what everybody uses. Hey, let's just use XYZ. Does not matter what it is. Let's just use it because labor is cheap. It's easy. My vibes, AI, big companies are doing it. Look at the success of so-and-so. Look at our competitors. Look at the group of people that we have who, like, all of these things are basically rooted in short-sighted viewpoints. It is extremely important. No, it is incumbent. It is your duty to take the time up front to make judgment values on what the hell you're doing and why. Unfortunately, We are lacking vastly in people who can make these value judgments up front. So we are stuck with people who don't have the ability to make these value judgments, therefore proceed with whatever is expedient, vibes-based, etc., for a number of other reasons, mostly psychological, mostly because they're babies. And the long-term consequences, most of them never have to deal with it because they've escaped the space to begin with by the time these things rear their ugly head. However, when it comes to something like the military or police or the things that operate in your day-to-day world for a long period of time and have a consequence on you or your loved ones, you don't get to escape it. Without accounting for military software acquisition and development, any explanation of accidents in software-intensive military systems is incomplete. In these early stages of system design, heavy reliance on contractors entails additional communication steps between software programmers and operators of deployed systems. Drawing on Nancy Levison's seminal work on software-linked accidents, one review of decades of research on this subject concludes, the source of most serious problems with software relates to outsourcing software development. I am going to yet again extend this argument. The source of most serious problems with software relates to outsourcing of thinking ability as part of your job as a programmer to an abstraction that tells you if you use X abstraction, you do not have to think about these problems. Regarding military accidents, the strength of these feedback channels between operators and software developers is crucial because they link military and civilian organizations that adhere to very different standards on system performance and reliability. This third approach, which I call software development lifecycle theory, highlights the impact of software acquisition patterns on the development of accident-prone systems. Military software development typically follows a linear waterfall model, which begins with system requirement specification and then progresses sequentially through system design, development, testing, and deployment. Within this process, evaluation and feedback from operators are limited to the late stages of development, by which time it is difficult to rework system concepts. This isn't just a military problem. This happens all the time in all aspects of software. You deal with problems as they come. You do not think ahead. You solve only the things that are in front of your face right now. Again, a number of reasons why, including external factors beyond just the programmer. But again, programmers do not have the ability. We have neutered the ability for programmers to even articulate why it might be important to deal with these things up front before they become a problem. What could be the problem even? What questions should we be asking about long-term future of the things that we're about to do? We don't even know how to ask these questions. As a 2010 National Research Council report notes, the Defense Department's acquisition practices for information technology are hampered by a serial approach to development and testing, the waterfall model, in which end-user participation often is too little and too late. Like water in waterfalls, operator input does not flow back up the chain of software development. These limited feedback channels between end-use operators and software developers produce more accident-prone military systems through three interrelated pathways. First, the waterfall method tends to produce human-machine interaction issues such as difficulty accessing critical data and unwieldy interface designs. Consider as an example one of the early interfaces for the Patriot system, which Dr. John K. Hawley, an engineering psychologist within the U.S. Army Research Laboratory, recalls was an error-prone interface based on his user tests. An insect could land on it, even, and change the settings. Yet, the interface was not fixed, in part due to the rigid sequential software development process established by Army senior leaders and the prime contractor Raytheon. Again, I can hear the rebuttal. This is a communication issue. We should be having the military open up more the dialogue between the people they work with to introduce these things and the people actually using them. Yes, these are all fair arguments. I'm going to extend the argument. The tech industry right now is rigid and does not want to have the communication that is required to have to produce better quality software, websites, and even hardware. And I think part of the reason why is because people do not want to deal with the problems that they know exist. Or worse, they don't even know that the problems exist. And so the entire industry becomes rigid and uncommunicative to people like me, because I am not alone. I am not the only 40-plus-year-old person who's been around the industry and seen the ebbs and flows and the stupidity go up and the stupidity go down over and over again on all these things. I am not the only person who's saying something about the state of the industry. And yet, most of the time, it falls on deaf ears because of the rigidity of the entire industry. Although you can make the same case here, as it appears, for the military. As Holly recounts, but they had already spent all this money on it, and so they fielded it. How many times has an executive board decided, well, it's too late for us to go back. We've spent a whole bunch of money on this React framework that is causing us problems. We're just going to have to deal with it. The soldiers are put into the position where they have to use it, whether they like it or not. Like, come on, this is not just strictly limited to military operations. This happens in the business world, in the world where you're building software or websites all the time. And again, I'm going to extend the argument. If we had programmers, junior or otherwise, who were encouraged and taught to even understand what questions they should be asking at the outset of whatever it is they're doing, these problems would at the very least become marginalized. Therefore, software can fail in the sense that it does not meet the needs of users, even if it passes all technical requirements established in the system acquisition phase. Studies by hand-computer interaction specialists have identified confusing interfaces as contributing to inadvertent military launches, fratricide, and other safety hazards. And you cannot tell me that the web has not become inundated with confusing user interfaces, especially with the advent of idiotic frameworks like React or Svelte or Vue or Solid, or all these things where these insane buzzwords that people use to make themselves feel comfy and smart and genius level, like signals and islands of reactivity and all this stuff. Like, what the hell is this crap? The simplest interfaces typically are the most well understood. You do not have to complicate these things. You're choosing to complicate them because you cannot deal with the fact that you've locked yourself in to anything but these idiotic complications. For instance, the lack of visual contrast between button interfaces for different settings has caused drone crashes. Flat UI, anybody? These human-machine interaction problems are intensified in high-stress scenarios when military operators must rapidly interpret data and make decisions. Second, limited operator involvement in the software design process leads to fewer opportunities to discover unanticipated vulnerabilities. As the Scud missile attack discussed above demonstrates, there are some contingencies that could be identified in the development process if software developers better understood how operators would likely employ a system. To address this issue, the Department of Defense has pushed for agile software engineering practices that involve rapid prototyping and early engagement with operators. Even if operators are sufficiently involved in the software development process, they still might not be able to anticipate all the scenarios under which the system will be used. Rebecca Slayton has showed that missile defense systems require vastly different software settings for field tests versus real-world use. Regardless, iterative software development practices can uncover more potential safety hazards than rigid sequential ones. Third, waterfall models of software development limit the capacity of military organizations and defense contractors to ameliorate issues revealed by the testing and deployment process. Unlike the hidden vulnerabilities issue discussed above, these safety risks are known. However, they remain unresolved because at this phase of the software development lifecycle, when end use operators point out hazards, it is too late, costly, and difficult to rework system designs. As one expert on human machine integration in military systems notes, by that time, most degrees of freedom for concept reevaluation or design changes have been lost. Okay. Take a sip there. Due to the inherent complexity and adaptability of software, the effect of system procurement practices on safety is especially salient for software-intensive military systems. As the three pathways illustrate, military software development presents unique challenges because it necessitates continuous adaptation to unanticipated vulnerabilities as well as end-use operator understanding of the system. For hardware development, sequential procurement approaches may be more suitable for managing safety issues since potential vulnerabilities and human-machine interaction effects are more predictable. There's a point that I'm going to bring out here, but I'm going to read one or two more paragraphs in order to get through this particular point. To reinforce this point, consider the difference between smart and normal or dumb refrigerators. When accounting for hardware failures in a normal fridge, manufacturers tend to focus on a limited set of physical or chemical mechanisms. For example, a puncture that results in gas leakage. Software-based smart fridges, on the other hand, present a wider range of failure paths connected to unpredictable human-machine interactions. For example, user forgets to connect fridge to a new Wi-Fi system, which causes temperature control software to malfunction. Software development lifecycle theory builds on the normal accident and high reliability organization approaches, which have broadened our perspective on software's role in military accidents, but also unearths overlooked causal factors. Debate between the normal accidents and high reliability organization camps tend to concentrate on whether accidents are inevitable in complex technological systems. Likewise, this clash has been adjudicated in military technologies by focusing on how military organizations operated and managed such systems after they have been fielded. Software development lifecycle theory brings the causal timeline of military accidents back to the initial phases of software design and requirement specs. Okay. Now, you can absolutely make a fair case for something like, well, a rigid waterfall approach where you do not account for user interactions before you get locked into a specific design paradigm of your software is inevitably down the road going to lead to issues. Yes, I agree. Therefore, let me extend this argument. Why on earth, then, if that is true, would you lock yourself in to a library, language, or framework based almost purely on vibes-based, productivity-based arguments? Especially when these frameworks have a decadal historical precedence of locking you in to the point where a simple one version upgrade from version 17 to 18, from version 18 to 19, necessarily dictates that you cannot move to the next version without an insanely serious lift most people cannot afford to take. You are handcuffing yourself such that you're locked in to an external factor that does not give a shit about the problems you're going to face or the problems your users are going to face. So by the time a problem pops up and somebody says, wait, even if we have a high degree of communication and everything's communicating really nicely and we're flowing and problems are being brought up and you're tackling them, at some point you are locked into this system. This system will change and that system does not care about the problems you have to face. It just doesn't. That system cares about the problems inherent to the system. These two things are not the same. System inherent problems, user inherent problems as part of the system you built on top of an original third-party system are not the same thing. Sometimes there's an overlap. Sometimes you get a thing fixed. Hey, that's great. Usually you don't. Do you even have the ability to understand what that problem might be? Can you articulate it? Can you talk about it? Do you know what questions to ask to potentially see down the road and determine whether you might be inadvertently handcuffing yourself to a bad situation? Again, I would argue most programmers have been neutered such that they cannot even fathom what that might look like to even begin to approach that problem before they write a line of code. That is fundamentally a much bigger issue than the code being produced, in my opinion, because there is, again, a logical entailment that if you do know how to ask those questions, you do know how to communicate those topics, then you are probably going to write more effective code that I and many others like me would prefer to see in the industry. Now, the rest of the article kind of breaks down further aspects of the approach that the author wants to take. So there are two initial aspects that are currently thought of as like the de facto way to determine why there might be software issues in military operations. The author is proposing a third and going over mechanisms and empirical data and case studies like we discussed as to why these problems present themselves. So they go over some evidence as to, well, is the theory of why these problems present themselves in military aspects even true? And there are some key points that I want to bring out. So, for example, when going into some of the case studies, here's one example of something that kind of correlates to the problem that the author is trying to describe. Paul Scher, I believe, for example, writes, "The causes behind the Patriot fratricides illustrate how normal accidents also can occur in military systems. This test's generalizability is enhanced because these cases also differ in many ways, including their operational context, level of complexity, the defense contractor involved, type of safety hazard, as well as other relevant military organizations." So he's essentially describing that just like in the programming world in general, military and just your regular programming job are not excluded from external factors having an impact on things that go wrong, software that goes wrong, even if you write really high quality code. My argument again is extended. We do not write high quality code. My argument is that most of the programming space is encouraged to not write high quality code, which simply further exacerbates existing issues on top of creating further issues as a result of not being able to create quality code. I would like to see that changed. The author goes over a few more case studies about what happened in official investigations in other military accidents and specifics on like the software and like how the software played a factor in the things that went wrong. Let me see if I can find. Okay, so this one's a good one. Let's just briefly go over this this example, because I think that this example I think this is the one I wanted to bring out. If you just replace the military nomenclature of the example with just your standard, I work at a company, I'm building a website, I'm building some kind of software, I'm doing XYZ, normal day-to-day stuff that most people go through. You can see how a lot of the nomenclature or terminology can be easily swapped out with something you might do. Okay. On July 3rd, 1988, the USS Vincennes, man, was passing through the Strait of Hormuz. Again, I'm butchering that pronunciation. Within Iranian territorial waters, to investigate reports of Islamic Revolutionary Guard Corps speedboats attacking neutral merchant ships. The Vincennes, I'm doubling down on the pronunciation, boasted an Aegis system, a highly sophisticated combat information center that automated functions such as target classification and target weapon pairing. I just want to reread that for emphasis. A highly sophisticated combat information center that automated functions such as target classification and target weapon pairing. That morning, radar operators in the Vincennes misidentified an Iranian passenger airliner as an Iranian F-14 Tomcat. So it's like a commercial, essentially, plane for a battle plane, to put it short. And the U.S. warship fired 2 surface-to-air missiles at Iran Air Flight 655, killing all 290 civilians on board. Before the July 2014 MH17 shootdown over Ukraine, it stood as the deadliest civilian airliner shootdown in history. How does a billion-dollar warship equipped with state-of-the-art software for tracking and classifying aircraft end up shooting down a civilian passenger plane? The official investigation, known as the Fogarty Report, revealed that the ship's Aegis system supplied accurate data to the Vincennes crew. The Aegis provided altitude information that the plane was ascending, like a commercial plane, not descending, like a hostile military plane. The crew, however, reported that the aircraft was descending as it approached the ship. There is much to be mined from the high-stakes calls made in these critical minutes, and the ensuing investigations and congressional hearings identified human error, including stress and psychological issues, as the primary cause. Fair enough. Yet, it is equally, if not more valuable, to trace problems with the Aegis further back to the decisions made about software design in the initial procurement phase. This would also cast attention on the companies that built the system, namely the RCA Corporation, which was awarded the prime contract for the Aegis in 1969. If software development lifecycle theory holds, the case evidence should show that the system development process factored into the Combat Information Center operators' struggles with managing Aegis-related risks. One of the key issues is whether the Aegis program managers in RCA gave sufficient attention to user interface considerations in tense combat settings. Matt Yaffe, a systems engineer at RCA in the mid-1970s, pushed for the Aegis display to include a rate of change indicator for altitude. On debates over this issue, Yaffe recalls, "I wound up literally screaming at my boss, 'You hired me for my technical experience and combat experience. If you're not going to listen to me, why don't you fire me?'" Anybody feel heard right now? Having previously served in the Vietnam War on ships equipped with forerunners to the Aegis system, Yaffe was one of the few people involved in Aegis software development with experience operating similar systems in high-stress environments. Without this rate of change indicator, controllers had to compare data taken at different times and make the calculation in their heads, on scratch pads, or on a calculator, and all this during combat. This increased the likelihood of misreading whether a ship was descending or ascending. These issues could be traced back to the extent, timing, and influence of feedback from military operators to software contractors in the system development process. The Aegis system was developed based on the Department of Defense's 1679A software standard, which heavily relied on the waterfall model and even restricted the ability of designers and users to collaborate and reverse initial specifications. As Yaffe states, when Aegis was being developed, it was being developed with a waterfall model. We drew up a software requirements spec document, sent it to the Navy for review, and they would come back for one meeting of a few hours. It's hard to do human-machine interface that way. Now again, I'm going to make an extended argument here because I can hear the rebuttal. Yes, but Spiro, this is another communication issue between contractors and military, people who use it versus people who don't, etc., etc. Yes, 100% agree. I grant you the entire argument. Here is my argument. We don't even know how to have these damn conversations to begin with today. Even if you had a magic button that would solve all communication problems in terms of removing any barriers to communication, whether it's something as simple as a basic website for a shopping like e-commerce system or a military industrial system, doesn't matter, magic button, remove the communication barrier. The amount of people who exist on this planet as programmers who have been encouraged, have had the opportunity, have been given the leeway that they need to become, say, exercised and well-versed in the job that they're supposed to be doing is few and far between, far fewer than it ever has been before. That is my argument. So even if you could remove the communication barrier, you would still have problems like this, because even if it could be communicated that there is an interface design issue, you still have long-term problems that you're not resolving up front. You're still going to have problems down the road that even if you have high levels of communication, you're probably not going to discover until farther down the road when it's too late to make the appropriate changes. And that's even if you have people who know how to tackle those changes when they need to be made to begin with. Furthermore, many actors had raised concerns that Aegis systems proceeded into production without adequate attention to testing and operator feedback. How many times have you heard that? Outside of military operations. A General Accounting Office investigation reported a long list of testing limitations to the Aegis system at RCA's facility in Morristown, New Jersey, such as the on-land location, lack of actual missile firing capability, and differences between the tested and fielded versions of the system. Now, I'm going to take this argument and I'm also going to extend it. I can hear the rebuttal. Yes, but these are actual missiles you need to fire. These things are expensive. Again, the military should open up the ability for the people who are creating software for these missiles or for these systems to use them in field and, receive feedback and make, agile testing. This is all great. I agree. Again, I grant you the argument. Here's the problem with today's programming world. 1, the amount of testing that we do today is not the same as the amount of testing that we would be doing if we cared more about the code that we were producing. Why do I say that? Because it is far too common for you to pull in an abstracted layer of something, library, framework, language, in order to solve and thereby rely. It is an implied, non-explicit, implicit reliance that someone has tested the problems that the abstraction claims to solve for you. Therefore, you do not test for those problems. What you test for is everything outside of the imported library, language, framework, or abstraction that you're using, because those are the things you care about. Otherwise, why would you bring an abstraction in the first place? So I would argue that fundamentally, we actually test for far fewer things than we ever have before, because we rely on the abstraction to have tested a problem and solve the problem. The realism of those tests have also been questioned. The test ranges were set up such that threats would only come from a predictable area. Moreover, certain events, such as aircraft leaving the immediate test area, tipped off crews that a test event would soon occur. Together, these conditions allowed crews to deduce the general direction, timing, and type of the test threats. Sources familiar with the classified version of the General Accounting Office report confirm that these so-called sea tests did not approximate a realistic, challenging combat environment. I am going to once again extend the argument. But Spiro, then the military should allow for better testing, be more stringent, etc., etc., etc. Great. Again, I grant you this argument. You are right. We both agree. The problem today is that we do not have people who are able to articulate the problem with testing software on the field. They don't even know how to begin to ask the question of how would you even test this in a real world scenario? How would I raise this problem? How would I think ahead beyond the 1 to 3 years that I'm going to be around in this company, or the 1 to 3 years that I'm going to keep hiring this person as a programmer, or the 1 to 3 years before we sell the company to a bigger company? We all make our money right off into the sunset. Then it's the bigger company's problem. You have these short myopic views that, again, even if you are aware of these problems and you want to tackle them, we have unfortunately neutered the people in our industry so that we cannot even begin to approach the problems in a well-versed way. We no longer have the experts who are capable of dealing with this. That is the underpinning argument of what I'm trying to present here. And once more, I want to emphasize that to get from we don't have enough experts to we do have enough experts is actually not that big of a jump. Most juniors are capable of asking the right questions. They just have to know what questions to ask just to begin with. Do they have to have the answers? No, not necessarily. But knowing what questions to ask is like the very first step that you need to be able to get to an answer. And then the hope is that if you have enough juniors who are trained appropriately, then those juniors are surrounded by intermediates and seniors who can tackle problems like what's happening in military operations like this one. And then they can say, hey, that's a good question. Let's solve it. Here's why we need to solve this problem, Mr. General, Admiral, Captain, doesn't matter who. We have to be sure that we're tackling these problems. Here's why. We don't have that right now. Okay, so the article goes on to describe some more of the case studies, including the Patriot friendly fire incident. Okay, I believe this is one I wanted to bring out. Let me just do a quick. No, I don't think it was this one. Although it is a good one to read. Essentially what happened was that Raytheon created a piece of software that was intended to identify friendly targets versus foe. And they made some assumptions and decisions during their software creation process and the internal exercises that they had. There, again, did not have enough ability to use real world scenarios to determine whether their system was performing the way it should have been. They met all the requirements they were supposed to meet. Again, this is an extended argument. You can do the exact same thing. You can do the exact same thing with web or software. Hey, we met all the requirements. You told us to do X, Y, Z. We did it. And unfortunately, it failed because in a real world scenario, the software didn't meet the actual standards, what would have been required to help someone who was operating one of these planes to identify the difference between foe or friend. And they unfortunately made an attack that they should not have made. So it's a similar type of thing. The collision of the USS McCain and the Alnick MC. This one is I will read this one. It is kind of an interesting one that has. This is kind of like the last thing that I'm going to read on this article, and then we're going to move to a few other topics that are related. This is more of like the introductory one. So on August 21st, 2017, the U.S. Navy destroyer John S. McCain made a sudden turn to port and unintentionally struck the Alnic MC, a Liberian registered oil tanker off the coast of Singapore and Malaysia, east of the Strait of Malacca. About an hour earlier, the destroyer's commanding officer, Alfredo J. Sanchez, switched the integrated bridge and navigation system to backup mode, setting off a series of mistakes that caused the hard turn. 10 U.S. Navy sailors died because of the collision, making it the Navy's deadliest accident in 4 decades. A number of investigations into the collision pointed to design flaws in the McCain's navigation system as playing a major role in the accident. First, in its backup mode, the system allowed crew from different parts of the ship to take charge of steering, which led to confusion over which station had thrust control for different propellers. Second, for steering commands, the system only provided touchscreen controls as opposed to mechanical throttles that gave more tactile feedback to operators. I just want you to soak that in for a second. You know what? I'm just going to repeat the sentence. Second, for steering commands, the system only provided touch screen controls as opposed to mechanical throttles that give more tactile feedback to operators. As the National Transportation Safety Board's investigation concludes, the design of the John S. McCain's touchscreen steering and thrust control system increased the likelihood of the operator errors that led to the collision. To be sure, issues with integrated bridge and navigation system development process could have been partially mitigated by improved decision-making on the day of the collision or better training in the months before. Fair argument, I agree. Ultimately, however, these design flaws were rooted in the proclivity of system designers to automate and digitalize navigation functions without sufficient attention to the needs of operators. According to operators interviewed in the Navy's investigation, they regularly disabled the system's touchscreen to avoid accidental rudder changes and ignored fault notifications due to displays that were difficult to interpret. I just want to read that one more time. According to operators interviewed in the Navy's investigation, they regularly disabled the system's touchscreen to avoid accidental rudder changes and ignored fault notifications due to displays that were difficult to interpret. I am going to extend this argument once more. Is anybody no. How many people are deeply aware of the issues that consumers have with these fancy new designs, because these fancy new abstractions make it easy to create these designs, these cookie cutter designs where you just get to do X, Y, or Z repeated ad nauseum. Everything looks this ad nauseum. Everything looks the same. Errors are weird edge case scenarios. The consumer doesn't understand what they're doing. And so they just switch off new features. I've heard this many times. People prefer some of the older websites or some of the older software because the new stuff sucks. They can't read it. They can't interpret it. They don't know how to use it. It's confusing, etc. Oh, but the developers got to feel nice and comfy with their vibes-based programming pushing it out. How many people are deeply aware of consumers' complaints about these new fancy ways to approach these problems? Let alone the loss of life consequences of implementing these things because you think it's the new fancy way to tackle these architectural software-based problems in military operations. You cannot sit there anymore. I have presented the evidence time and time again. This is not the first time. These things have real-world consequences. People lose their lives because of your vibes-based programming. If you don't agree, you're a piece of shit. You can't deny these claims anymore. And if you continue to deny them, fine. But pretty soon, these things are going to snowball to the point where everybody's going to see it for what it is. And again, to go back to what I said at the beginning, I think that time is coming far sooner than all of you think. And you're going to be up. You're going to be put up to have to defend the actions you took for your feelings and your preferences and your subjectivity and your business value and your ship it and your AI slop and all of these things. You're going to have to answer for that. Thank you for gifting that sub out, Paddle Gnome. I appreciate it. Tversky. And Leather Soup, thank you for the follow a few minutes ago. I appreciate that too. So I think Battle actually brings up a good point here. These innovations aren't for the end user. They are for the appraisal and accolades from their engineer peers. I think Battle nails it. It's definitely a key aspect to the decisions being made, the technological decisions being made by programmers who perpetuate these idiotic ideas. And it is, in part, that. It garners you the positive pat on the back attention that people seek within the community. And I am challenging everyone to counter that narrative. You do not need that pat on the back. The pat on the back does not come from doing the things that everybody says you should be doing. The pat on the back comes from asking appropriate questions, whether those questions lead to the same answer as you would have got to anyways at the beginning or not. Knowing what questions to ask are fundamentally far more important than doing and going along with status quo. And that will garner you much more respect. Because if you ask the right questions, people will see the problems that were avoided by asking those questions. But it means that you have to know which questions to ask. It means that you have to push yourself to understand more than the abstraction that you are accustomed to working in, that you are told to work in, or that your favorite tech influencer tells you to work in, or that management or your colleagues tell you to use because it's just the way of life. Unfortunately, that's part of your job, or fortunately, it is part of your job. We may need to define vibes-based programming. So it'd be something along the lines of, I don't have an objective reason to use something or execute a particular paradigm in my code, except for something that's subjective to me. For example, readability. People claim readability all the time. So they might say something like, I find TypeScript to be more readable because I understand the types that I'm intended to use versus vanilla JavaScript, where the types can kind of be wishy-washy, or I can make my own interpretation of these input parameters for a function need to be an integer versus a string. It's kind of up to my interpretation based on how I read the function. So there is a subjective readability preference. However, for every subjective readability preference, you can always find somebody with the opposite subjective readability preference. You will always find someone who, for example, finds TypeScript to be far less readable than JavaScript and have no problem dealing with type safety in vanilla JavaScript versus TypeScript, and might even, in fact, make a subjective argument that they find it harder to deal with types in TypeScript, say because of the use of the word any, which is like the antithesis of type safety to begin with. That's just an example. There are many such examples like that. For example, the difference between using, say, ORM in PHP, which is Object Relational Model, for doing SQL queries. Some people find that far more readable than raw SQL queries. Other people would subjectively say, no, I find it more readable to do the raw SQL queries because I can read the raw SQL queries better than whatever abstraction ORM you're using, and vice versa. These are all subjective things. And the subjective factor comes into things like, am I doing what everybody else around me is doing? That's part of vibes. Does it make me feel good and productive to do the thing that I find subjectively to be positive? Those are vibes. You are going to be very hard pressed to find somebody who can make an objective, metrics, scientific, academic, or even just logical based argument as to why TypeScript is better or not, without any subjectivity at all. I have done that. I have on previous streams gone over whether TypeScript is actually better than vanilla JavaScript. In some cases, it's about the same. In some cases, it's worse. Those are objective metrics that have been done, though. Most people don't go that far. Most people go with the vibes, which is a subjective. This is how I feel. This is what I like. This is what people around me like, etc. That's vibes-based programming. I feel good doing this thing. It's not objectively good. It's not objectively performant. It's not objective quality. It's subjective. Okay. I believe this was everything that I wanted to read from this article. The Afghanistan withdrawal goes into the Kessel Run software. If you don't know what that is, it's it's an error. It basically just like plans out the flight routes and stuff of different airplanes, so that it can like mitigate accidents, crashes, things like that. I don't believe there was anything in here that was new that we haven't already covered in terms of principal topics. It's more about like actual like operational use, high stress situation, what the software actually does in practice versus in testing, etc. And then the conclusions based on that are obviously more communication and more upfront awareness of what it is that the military is bringing on board into their internalized mechanisms. But again, I'm going to say it one more time, and then we'll put this article to bed. The argument can be extended for anything you're doing. You should be as aware as you possibly can be of the long-term consequences of the abstraction that you're bringing in to the paradigm that you're trying to solve.